Okay, so just a quick recap of what I was talking about while I was not recording. The homework to has been posted on Canvas, and the slides for Lecture 2 have been posted as well. So just a quick review of our X-ray, or this really goes for any interaction of X-rays, which is what we use for imaging with the material. We ultimately have to go, so two things. There's a wave, incoming wave, or photons, we imagine them as a wave, electromagnetic radiation, and that wave has certain wavelength, and basically that wavelength decides what is the resolution of things that we can see with that wavelength. So that is the number one. Now, number two is that those waves carry certain energy, and as they do, they interact, and they interact with the material. They interact with the material on an atomic level, essentially. Though when we look at the cumulative effect, we kind of average that over a certain area, which is our imaged voxel, right? Our imaged numerical cell. Now, the simplest way that we imagine that they interact with this material is that we have an incoming intensity, and as I go through certain material thickness, so this is specifically for X-rays, as I go through certain material thickness, okay, I'm going to attenuate, so what comes out is lesser. And the model that we use for the intensity is this exponential model, so I depend on the thickness delta x, and I have certain a coefficient, which is here just simple coefficient mu. Okay? So that mu basically comprises this entire interaction of the X-ray with the material. And in the most simple case, I just have this constant mu. And things then stack up, right? So they add up. So if I have a thicker material of the same intensity, I'm just going to have a different delta x here, or 4 delta x in this particular case. And that's going to reduce my intensity according to this law, which is called Lambert-Beer's law. And if I have different materials, I'm just going to add things up. So delta x of one type of material plus delta x of another type of material, and so forth. Okay? So that's sort of, this is the things, like if I have different materials, I kind of just add them up. This is simplified view of things. This coefficient really embraces a whole lot of things in there. So when a wave comes in, I could interact, and at low energy, I might just have some emission of electrons from this material, okay? And those are called photoelectrons. At some sort of mid-level energy, I'm going to have some form of scattering, and it could be elastic or inelastic. And I kind of combine both for most of the energies that we are thinking about. Okay? So there is, for elastic, I just, incoming wave is kind of the same as the outcome, it just bounce off. But in reality, that never really happens. Some of that energy is absorbed in the material, so I never bounce off the same that I came in. Okay? And that can be larger or lesser. And then you emit some different type of energy as you go away. And at high energy, you might even emit some more particles. Now, this mu is kind of sum of this linear attenuation coefficient is sum of all of these. And I'm not going to go into details, but essentially I depend on the energy and the atomic number, what is the density of electrons in the material, and overall, so what it is that I'm encountering and how many electronic clouds am I encountering. And that this is still a model, right? So we basically fit these coefficients, and these coefficients are found by a hard work of trial and error of researchers over a long time. Okay? Now in tomography, and this is the exercise you're going to get, so technically we project. So we have beam, and the geometry of the beam does matter. So let's say in the simplest case, I'm passing through material, and there is a detector here that we are detecting these coefficients, and I need multiple projections through the material in order to basically reconstruct what is happening in the three dimensions. Otherwise, I'm just looking at the projection. Great. So that math was worked out initially in 1917, but was forgotten until the systems were actually built who could do that. So Radon started, but it's Cormac and Hansfeld that redeveloped it in 60s. So this is a simple view of a parallel beam going through material of 4 voxels. So basically, the things will stack up. On average, I have a mu1 in this voxel, and mu2 is another voxel, and that's averaging everything that is happening in that material. In porous media, that's not necessarily simple because I have fluids and solids and multiple possibly fluid phases and multiple mineral phases that are interacting and averaging over this little area or volume. Right? And you will get this as an exercise to kind of understand how the math works out for setting up this system of linear equations. Okay, so that's just a quick summary. And then always understand that this voxel or pixel, it does have sort of finite volume, and you're averaging over that volume, whatever that volume might be. And often you will not necessarily have equal x and y and z directions, so you're kind of averaging over a larger slice. And that is really true for any effort, any modeling effort. We're always kind of like having these boxes of material, right, where we are developing our equations for. Now, in terms of lab systems, we have seen some of them. So this is basically very similar to the one that is downstairs in Dr. Espinosa's lab. A lot of systems are now available for about $500,000, which in terms of research dollars is not terrible. A research group acquires that and then uses it, and multiple research groups use it over time. And you need, for this reconstruction, you need to have a computer attached that is doing the reconstruction, especially if the systems are larger. And it's here we have it in the Department of Geosciences, which we didn't visit, but it's a larger NSF-funded, NSF is National Science Foundation facility. And then in our own department, which is mostly work of the research groups that are affiliated with our department, we have one X-ray system, that is the medical CT that we visited in Dr. DiCarlo's group, and another one in Dr. Espinosa's, which is micro CT. Okay? So in medical scanners, you have this source, and we have seen this version of this in DiCarlo's lab. You have source and detector kind of moving around a person, or in our case, a core, rock core. And since we don't care about hanging rock cores, we can, insert them vertically as well as horizontally. For a person, you put them on a horizontal thing, but this is on a horizontal bed and move in and out. This is how it actually looks like when you open it up inside. Okay, that's the part that is covered up that you don't see, but that's basically you have this source and detector that is moving around an object, okay, and collecting projections. So this is basically this conical geometry. And this geometry determines how do you reconstruct. So in your homework, you're not going to get conical geometry. You're just going to get simple parallel beam just to get the feel of how these things are reconstructed. But ultimately, you need to know the geometry to reconstruct in 3D. Now, in general, what you're working with is you have a certain intensity of the X-ray, okay? And you need to kind of focus it through a spot. And that spot will be the spot that you're focusing it through, either as a source or as a parallel beam, determines then also what is going through the object that you want to image, right? So if you want to image smaller and smaller, you have to be able to focus that spot smaller and smaller. Right? So whatever X-rays are generated, they kind of need to be focused, either as a source, a point source, or as a parallel source. So that's typically in the realm of physicists. They often construct these systems and improve, right? And you need to basically minimize the radius and also focus the power that is going through. Okay? And the problem of this flux that is going through is essentially that if you have energy that is high, it's kind of never happy, and the optimum is not easy to find. If you have too high of an energy, you're simply going to pass through the material, whatever the material is. And you might have high density, low density, you're just going to pass through. So you're not going to get enough contrast between two different materials of two different densities. And especially if you're in our applications, oil and water, we want a lot of contrast. It's not going to be enough. Okay? On the other end, if you have too low of an energy that would kind of have the time to inspect the different contrast, you're not going to get enough of it through the material. So your statistics on the other end that you're collecting is not going to be good. So then you're going to have the signal that is relatively weak and very susceptible to noise. So then like you kind of play in between the two. And then what we also know is that for low energies and high energies, we're going to have different interaction with the material. Okay, and different effects are important. So there's this optimum beam energy for every different material. And that's the difficult part because materials are not all the same. So there's a whole lot of trial and error. Now there's another thing is there's so-called two different effects at play in X-ray. So if you have a photon flux or any kind of electron passing by a nucleus, because of the opposite charges, you're going to have a slowdown due to the attractive force. And if you have change in acceleration or velocity, that's going to change the electromagnetic radiation as well. So that's called so-called breaking. In its original is in German, Bremsstrahlung. So that is the Bremsstrahlung radiation that shows up when you're detecting on the other end after the interaction happens. So that sort of, depending on the energy that you're doing, you're going to see the spectrum of intensities that are resulting just from that. The second thing that can happen is so-called characteristic radiation. So this is when you actually knock an electron out of its path. And because of that, you're going to have characteristic X-rays emitted. Okay? So if you think about basically electrons moving in different shells or orbits, as they change, when you knock one out, they change the energy, right? So you go from one to the other. And that difference results in emission of X-ray as well. So you're going to see that. But that's not going to happen. That's kind of happens only at specific energies. You have to have the correct energy for that to happen. And that energy depends on the material or the atom that you're encountering. So those characteristic X-rays also often then enable us to characterize materials. Okay, so you're going to have basically, because of that, we can actually do, or even in thin section analysis, we can actually go and figure out what are the materials that we actually have, or what are the minerals that we actually have. Okay. So these are kind of discrete. Okay. So then when you combine the two, you will get something depending on the energy that you're using. You're going to have something like this as a produced combined intensity. Okay? So we often then image a different energies, and we have, this is what you effectively see. So these sharp peaks in the produced energy, depending on what energy you're using for your X-rays, are characteristic X-ray radiation. So you can kind of go above and below of the characteristic X-ray for a different material. So there's different things that you're going to see using that energy. Okay. So that is right now used as dual energy CT. So basically as a type of routine, you will go through the entire core of material and you're going to image it at two different energies. Now those are typically picked, say 100 and 140 kiloelectron volts. And then basically based on the differences in those two images, you can see whether you have certain materials or not, and you can use those differences to inspect and better reconstruct what's actually in the material. This was actually in the part of the thesis work of my former student, Rodolfo Victor. And the data is actually on DigitalRocks portal. So that can improve identification in images. And these are called edges. So different energy, you will see different type of material simply because of this characteristic energy that is emitted or not. Okay. Now, let's lighten this up a little. So X-ray is not used just for scientific purposes. It can actually be used for artistic purposes. And I like this video because kind of reviews also what is possible to do with X-ray. So I'm going to play it here. Do you all watch TED Talks? If it's going to play, come on. Really? Maybe it doesn't like full screen? Oh, come on. It is an HDMI. No.
Head and the...
Okay. Something's not. It's playing. Okay. This is interesting. Play. Okay. This is Edge, is it? Yes. Let's go to Chrome. Or no, Facebook. Not Facebook, Firefox. And I'm gonna kill this one. Try now. What do you know? Firefox works better on a Windows machine than Edge.
Dr. Röntgen x-rayed his wife's hand, Quite why he had to pin her fingers to the floor with her brooch, I'm not sure. It seems a bit extreme to me, but that image was the start of the X-ray technology, and I'm still fundamentally using the same principles today, but I'm interpreting it in a more contemporary manner. The first shot I ever did was of a soda can, which was to promote a brand that we all know, so I'm not going to do them any favours by showing you it. But the second shot I did was my shoes that I was wearing on the day, and I do really like this shot because it shows all the detritus that's sort of embedded in the sole of the sneakers. It was just one of those potluck things where you get it right first time. Moving on to something a bit larger, this is an X-ray of a bus, and the bus is full of people. It's actually the same person, it's just one skeleton. Back in the 60s, they used to teach student radiographers to take X-rays, thankfully not on you and I, but on dead people. So I've still got access to one of these dead people called Frida. She's falling apart, I'm afraid, because she's very old and fragile. But everyone on that bus is Frida, and the bus is taken with a cargo scanning X-ray, which is the sort of machine you have on borders, which checks for contraband and drugs and bombs and things. Fairly obvious what that is. So using large-scale objects does sort of create drama because you just don't see X-rays of big things that often. Technology is moving ahead, and these large cargo scanner X-rays that work with a digital system are getting better and better and better. Again, though, to make it come alive, you need somehow to add the human element, and I think the reason this image works, again, is because Frida's driving the bulldozer. Quite a difficult brief, make a pair of men's pants look beautiful, but I think the process in itself shows how exquisite they are. Fashion. Now, I'm sort of anti-fashion because I don't show the surface, I show what's within. So the fashionistas don't really like me because it doesn't matter if Kate Moss is wearing it or if I'm wearing it, it looks the same. We all look the same inside, believe me. The creases in the material and the sort of nuances, and I show things for really what they are, what they're made of. I peel back the layers and expose it, and if it's well made, I show it. If it's badly made, I show it. And I'm sure Ross can associate that with design. The design comes from within. It's not just top show. I get some strange looks when I'm going out getting my props. Here I was fumbling around in the ladies' underwear department of a department store, almost got escorted from the premises. I live opposite a farm, and this was the runt of the litter, a piglet that died. And what's really interesting is that if you look at the legs, you notice that the bones haven't fused, and should that pig have grown, unfortunately it was dead. It would have certainly been dead after I x-rayed it with the amount of radiation I used anyway, but once the bones are fused together, it would have been healthy. So that's an empty puffer jacket, but I quite like the way it's posed. Nature is my greatest inspiration, and to carry on with a theme that we've already touched with is how nature is related to architecture. If you look at the roof of the Eden Project or the British Library, it's all this honeycomb structure, and I'm sure those architects are inspired, as I am, by what surrounds us, by nature. This, in fact, is a Victoria water lily leaf that floats on the top of a pond, an amaryllis flower looking really three-dimensional, seaweed ebbing in the tide. Now, how do I do this and where do I do this and all that sort of thing? This is my new purpose-built X-ray shed, and the door to my X-ray room is made of lead and steel. It weighs 1,250 kilograms, and it's the only exercise I get is opening and closing it. The walls are 700 millimetres thick of solid, dense concrete, so I'm using quite a lot of radiation, a lot more than you'd get in a hospital or a vet's. And there I am. This is quite a high-powered X-ray machine. What's interesting really about X-ray really is, if you think about it, is that technology is used for sort of looking for cancer or looking for drugs or looking for contraband or whatever, and I use that sort of technology to create things that are quite beautiful. So still working with film, I'm afraid. Technology in X-ray, where it's life-size process, apart from these large cargo scanning machines, hasn't moved on enough for the quality of the image and the resolution to be good enough for what I want to do with it, which is show my pictures big. So I have to use a 1980s drum scanner. It was designed in the days when everyone shot photographs on film. They scan each individual X-ray, and this shows how I do my process of same-size X-ray. So this is, again, my daughter's dress. It still has the tag in it from me buying it, so I can take it back to the shop if you didn't like it. But there are 4 X-ray plates. You can see them overlapping. So when you move forward from something fairly small, a dress which is this size, onto something like that, which is done in exactly the same process, you can see that that's a lot of work. In fact, that is 3 months solid X-raying. There's over 500 separate components. Boeing sent me a 747 in containers, and I sent them back an X-ray. I kid you not. Okay, so Frida is my dead skeleton. This, unfortunately, is basically two pictures. The one on the extreme right is a photograph of an American footballer, the one on the left is an X-ray. But this time I had to use a real body because I needed all the skin tissue to make it look real, to make it look like he was a real athlete. So here I had to use a recently deceased body, and getting hold of that was extremely difficult, laborious. But people do donate their bodies to art and science, and when they do, I'm in the queue, so I like to use them. The colouring. So colouring adds another level to the X-rays. It makes it more organic, more natural. It's whatever takes my fancy, really. It's not accurately coloured to how it is in real life. That flower doesn't come in bright orange, I don't think, but I just like it in bright orange. And also with something technical like these are DJ decks, it sort of adds another level. It makes a two-dimensional image look more three-dimensional. The most difficult things to X-ray, the most technically challenging things to X-ray are the lightest things, the most delicate things. So to get the detail in a feather, believe me, if there's anyone out here who knows anything about X-rays, that's quite a challenge. I'm now going to show you a short film. I'll step to the side.
The thing in there is very dangerous. If you touch that, you could possibly die through radiation poisoning. In my career, I've had 2 exposures to radiation, which is too many because it stays with you for life. It's cumulative. It has human connotations, the fact it's a child's toy that we all recognise, but also it looks like it's a robot, and it comes from a sci-fi genus. It's a surprise that it has humanity, but also man-made future alien associations. And it's just a bit spooky. Fibre proposal for a load of it. I don't like it anymore, because then the bus was done with a cargo scanning X-ray machine, which is used on the borders between countries looking for contraband and illegal immigrants. The lorry goes in front of it and it takes slices of X-rays through the lorry, and that's how this was done. It's actually a slice. It's a bit like a CT scanner in a hospital. Slice, and then if you look carefully, there's all little things. He's got headphones on, reading the newspaper, got a hat on, glasses, got a bag. So these little details help to make it work, make it real. The problem with using living people is that to take an X-ray, if I X-ray you get exposed to radiation. So to avoid that, and I have to avoid it somehow, is I use dead people. Now, that's a variety of things, from recently deceased bodies to a skeleton that was used by student radiographers to train in taking X-rays of the human body at different densities. I have the very high-tech equipment of gloves, scissors and a bucket. I will show how the capillary action works, how it feeds. I'll be able to get all the cells inside that stem because it transfers food from its roots to its leaves. Look at this monster! It's so basic, it just grows wild. That's what I really like about it, the fact that I'm going to go and buy it and it hasn't been genetically modified at all, it's just happening. And the X-ray shows how beautiful nature can be. Not that that is particularly beautiful when you look at it with a human eye. The way the leaves form, they're curling back on each other. So the X-rays will show the overlaps and these little corners. The thicker the object, the more radiation it needs and the more time it needs. The lighter the object, the less radiation. Sometimes you keep the time up because the time gives you detail a lot. The longer the exposure goes on for, the more detail you get. If you look at this just the tube, it is quite bright. But I could get a bit darker in the tube, but everything else would suffer. So these leaves at the edge would start to disappear. What I like is how hard the edges are, how sharp. Yeah, I'm quite pleased with that.
This is the play with the intensity.
I travel beyond the surface and show something for what it's worth, what it's really made of, how it really works. But also I find that I've got the benefit of taking away all the surface, which is things that people are used to seeing.
And that's the sort of thing I've been doing. I've got the opportunity now to show you what I'm going to be doing in the future. This is a commercial application of my most recent work. And what's good about this, I think, is that it's sort of like a moment in time. Like you've turned around, you've got X-ray vision, and you've taken the picture with the X-ray camera. Unfortunately, I haven't got X-ray vision. I do dream in X-ray. I see my projects in my sleep, and I know what they're going to look like in X-ray, and I'm not far off. So what am I doing in the future? Well, this year is the 50th anniversary of Sosagoni's Mini, which is one of my favourite cars. So I've taken it apart, component by component, months and months and months of work. And with this image, I'm going to be displaying it in the Victoria and Albert Museum as a light box, which is actually attached to the car. So I'm going to saw the car in half down the middle, not an easy task in itself. And then so you can get in the driver's side, sit down, and up against you is a wall. And if you get out and walk around the other side of the car, you see a life-size light box of the car showing you how it works. And I'm going to take that idea and apply it to other sort of iconic things from my life. Like my first computer was a big movement in my life. I had a Mac Classic, and it's a little box, and I think that would look quite neat as an X-ray. I'm also looking to take my work from the two-dimensional form to a more three-dimensional form. And this is quite a good way of doing it. I'm also working now with X-ray video, so if you can imagine some of these flowers and they're actually moving and growing, and you can film that in X-ray, it should be quite stunning. But that's it, I'm done. Thank you very much.
So again, this video has a bit of an artistic flair, but all the components in what is he looking for, how does he get the contrast, are actually there, just like in our scientific applications. So just to kind of take you out of the out of the scientific context that we had into something a little different. Again, technologically, he's using X-ray just like scientists do. Now we get out of this. So let's back to the I will need to plug in my PC soon. So just a quick quiz to see whether you were paying attention. So how long did it take to X-ray Boeing? 3 months, part by part, and then juxtapose. True or false? The X-ray image of the player on the left was done in the middle of the football game. False. We can't X-ray people without really killing them. So not with the amount of detail that is shown here. And then true or false? Delicate light objects are the most difficult to image in detail. Partly because as you get good contrast on one end of it, you will lose contrast on the other. Okay. All right. Okay. So just a quick, we've been through all of this. So just to review once again, you might have different types of beams depending on the configuration. And this is actually from the paper that I have assigned for homework. So you might have a parallel beam going through. This is very common in synchrotrons, and that's going to be reviewed next. this fan beam or cone beam are more common in actual lab settings like the one we've seen downstairs. So voxel size that changes here from between the point source and the detector. Basically, you can play with moving the sample closer or further away. And then with the turntable, you get different projections. And this basically the ratio of R and L gives you the magnification that you see on the detector. And the resolution is what basically it's this detector pixel size divided by magnification. That's the best you can get in terms of resolving a detail. Okay, so this distance gives you the magnification, and then detector itself has certain sensitivity, right? And there is a pixel size on the detector itself, just like on this screen, and that you divide that by magnification, which gives you the ultimate resolution. Okay. Now, this maximum resolution is also related to the spot radius. Okay? So ultimately, you get the following formula as resolution. So this is flexible because you can put it in the room and you can play with it just like with the cameras in general and magnification in the cameras. However, if you have a very high angle of this cone, then your geometry kind of falls apart and it's hard to reconstruct in detail. So this should be as small of an angle as possible. Okay. One of the latest and the greatest is helical or spiral scanning. So you have a specific helical path that your detector and the source are moving on together, right? And that allows you to basically shorten the time of scanning required to actually get the image. So first one, it was invented in 1994, but for the microtomography applications in porous materials, it was first demonstrated in 2010 at Australian National University. And right now, this system is actually being sold commercially. So the problem, and this is the problem of, so you can actually get quite a long core scanned. The problem remains actually once I have a very large image, how do I analyze all of it? Okay. So if anybody is actually interested in papers on this, I can provide. Now, in terms of synchrotron, it's basically what you need is a particle accelerator to actually produce the electron beams. And at the same time, you need a sort of super microscope to see the results. So I'm going to move through. So in synchrotron, so this is basically the conventional X-ray. You basically get a much stronger intensity because you are more focused and you're using more of the same energy. So there's not many types of the energy is you don't interact with the large values of or a large array of energies. You don't have a polychromatic, but you have a monochromatic beam. So this is how a synchrotron actually looks like. So this is the particle accelerators, okay? And all of these are the stations where with the magnet you actually focus that beam into the station so you get this parallel beam. Okay? So it's way stronger energies, and you actually, as researchers, come into all of these stations individually and basically do their scanning. And you typically can reserve this facility for about up to 2 days. So whatever experiment you had in mind, you have to set up and have executed in 2 days. And Javier is kind of smiling because it takes a lot of trial and error. So you have to have first try it out at home, then get on the plane, and then go there and set it up and kind of pray that it goes well. This is, yes, as it's working. right? So these are typically specialized for different type of applications, okay? But basically, you kind of reserve these stations to get the access. And there's actually another little video, so I hope my... so you get this parallel beam and sort of a more focused monochromatic X-ray with very high intensity. So that gives you different results. And that's favorable for tomographic images. You get pretty high resolution, high contrast, and no beam hardening because you don't have different types of X-rays going through, so you don't filter them in a sense. Okay, you have only one. And you have much higher photon flux. And you can still apply the same thing like dual energy scanning and so forth as you can for the other one. However, you do that for fairly small objects because you have a pretty high intensity because of the small beam size. So typically you will go and do this for objects that are 5 to 50 millimeters width. Now, in the setup that we have seen downstairs, it's you kind of whatever you can put on that turning table that can be much larger. Okay. Now, there's actually a video, and again, I hope that my so this is from Oregon State University. Dorte Wilderschild is one of the authors of the paper that you're going to review for homework. And this was filmed by Anna Herring, who is now postdoc at ANU. She was doing her PhD research project. Working things out locally in the lab.
Like the legend of the phoenix, all ends with beginnings. What keeps the planet spinning? The force from the beginning. Love. We've come too far to give up who we are.
These were done at a higher pressure. This is that perimeter. You can ride a tricycle or a bicycle.
She's up all night to the sun. I'm up all night to get some. She's up all night for good fun. I'm up all night to get lucky.
This is one of these stations.
We're up all night to get some. We're up all night for good fun.
I was supposed to interview you. Anna here is going to explain what we're going to do right now.
So nothing is working. Okay. We know there's a leak somewhere in this line because we've had 2 experiments fail already due to pressure drops in that line. We have no idea what the leak is, and we've been looking for it for 2 days. So now we're just gonna take everything apart and put it back together and hope that fixes everything.
Classical
And we hope
plumbing
it
problem
doesn't,
is just
so
a
much
micro level, right? There's a
Really
leak.
great.
In your research, there's either a leak in your lines or there's a bug in your code.
She's up all night to the sun. I'm up all night to get some. She's up all night for good fun. I'm up all night to get
So you show up early, you set it up all so it's not leaking on something that you can move into the beam. And
we're up all night to get lucky. 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 We're up all night to get
see the pump?
We're just waiting for everything to equilibrate, and I'm pretty bored, so I'm taking out the bicycle for a ride.
Song, she's up all night for good fun. I'm up all night to get lucky. We're up all night to the sun. We're up all night to get some. We're up all
You
night
can
for
see
good
the
fun.
stand.
We're up all night to get lucky. We're up all night to get lucky.
Searching Station D. Exit immediately. Searching Station D. Exit immediately.
We're up all night to get lucky. We're up all night to get lucky. We're up all night to get lucky. We're up all
So here you can see the dark color, that's supercritical CO2 within the pore structure of the rock. You can see rock grains here, and you can also see brine that shows up as a lighter color inside the rock.
all night to get lucky. We're up all night to get lucky.
There is never enough time. We just need more beam time.
So the essential problem is the same. Whenever you're using a user facility, you have to have your experiment set up outside of wherever it is that you're imaging, and then you have to be able to fit it in the imaging area, right? And then move it outside and after imaging. And if you're possibly doing your experiment outside, you cannot do it in the X-ray. So for that, the X-ray setup has to be adopted. Then if you're going in and out, and you're, let's say that you're having fluids, right? They're gonna move through as you're putting the core inside and outside of the setup. That's a problem. Right? So there's a lot of practical issues so it's always the best if you can actually perform the entire experiment inside of the X-ray without changing anything, but because of the different practical considerations that might not be possible, right? So if you're working on a very high pressure and temperature, then you technically have to run things in the oven, and you might be able to image it only after you open that up and move your setup, right? So there is always certain consideration. If you can, there are now combined, but those are inside or within certain research groups, combined setups where you have X-ray and the oven all in one. So you can take images as your experiment is going on in the oven. Right? Same goes for triaxial. Is that coming online anytime soon, Javier? Yeah. Combination of X-ray and triaxial. So if I'm fracturing, can I take that image at the same time without taking the core out? Okay. So a lot of times now imaging is done after the fact. You've done something, then you look at the sort of a result. So that's something to think about when designing these experiments. All right. So you have, this is the actual experiment going on inside of the beamline, and that's on the centimeter, order of centimeters. And then your results, these are basically post-processed results. This was in a bead back. You can see pendular rings of a fluid in between two different spheres that were post-processed to be actually visible, right? So equipment has to be, this acceleration happens on kilometer scales that produces very high intensity X-ray. Then your experimental equipment is basically on millimeter to centimeter scale, and that in order to get micron resolution. Okay? So that's something that synchrotron microtomography facilities enable. All right, so that's going to be end of that. My next plan is to, I saved what I needed to save. I'm going to stop a little earlier, but since we went overboard with our visits in the previous two times, that's going to be fine. I'm going to spend a little more time just giving you an idea what type of information you get with SEM versus X-ray for the rocks, because that's some of the most common applications, as well as a little bit more about the noise and contrast, because we're going to use that when we start filtering images for noise. So a little bit more, there will be a little bit more expanded, and we're going to go over that next time. All right.